but I am going to show that we are 17, 5, and 6. So, is this model up here, let's say we have 5 possible outcomes. Is this an appropriate model to determine a choice with 5 possible outcomes? No? Who said no?
I said yeah.
You said yeah? Why yeah?
Because there's 5 spaces.
There's 5 spaces. Okay, there's 5 spaces, and every space has an even amount of space taken up on the spinner. So Nate thinks it's fair. Olivia?
I don't think it's fair because there are only 2 different possible outcomes.
This spinner might have 5 spaces on it, but it's only showing 2 possible outcomes. It's only showing a red outcome and a blue outcome, and the red outcome in this model has a 3/5 chance. The blue outcome in this model has a 2/5 chance. So first off, this is not a fair model. Red and blue do not have equal probabilities. And this does not actually model this does not model 5 outcomes. It models 2 outcomes. So you have to be careful when you're setting up a probability model that you choose an accurate model for your situation. Come on. So we have a probability model, and it's going to show a video, for 6 possible outcomes.
Wow. What's the probability of that? Oh, come on now. This is getting ridiculous.
Have you ever had something happen like that's really rare, and then something else happen that's really rare, and you're like, wow, 2 rare occurrences. Like, what's the odds of that? Okay, that's not rare. So I'm going to move it back into our notes just so we can move a little faster. Nope. Don't give me the Word doc. No one likes Word docs. So, if we want the probability of getting fewer than 3 shapes, is there actually 1 card out of 3 cards? The probability is 1/3, but is it actually 1 card out of 3 cards? No, this is a reduced probability. So, which list of probabilities does not complete a probability model? Now, what does it mean to complete? What does it mean to complete the probability model? We talked about this last week. So finish, but in a probability model, what makes it finished? So I bet you'll be able to figure this out once we look at a list or 2. The first list says, what's your probability of getting fewer than 3 shapes? Fewer than 3. Okay, 1 or 2. 2 out of 6. That covers it. I reduced that. Probability of getting at least 3. At least 3 covers 3 or 4 or 5 or 6. So that's all of those. Does this look like it is a complete probability? So hang on to that thought. I'll put it on the TV for you. Now let's look at list 2. List 2 says, what's your probability of getting a fish? Well, here I have a fish, and here I have some fish. What's the probability of getting an apple? Well, here I've got apples, apples, apples. And the probability of getting a leaf, well, here's some leaves. Does that look like a complete probability list? Keep that in your brain. Sorry, I can't have both on the TV at the same time. So now my third list, probability of getting an even number of apples. Even number of apples, not an even number of apples. Probability of getting an odd number of apples. Okay, odd number of apples. Do you think that's a complete list? So what can we infer we're actually talking about here with a complete list?
Where all of the possible outcomes are accounted for.
Okay, and each of them is only counted once. So when we talk about a complete list, trying to wait for this to capture, a complete list is where every outcome is counted once. Guys, that's right here. Your complete, what complete means, each outcome in the sample space is exactly one event. They're all counted once, and the probabilities must equal 1 when we find the sum. So another way to remember complete, every option counted once. So list 3 here is a bad list because not every option or every outcome gets counted. Now, none of them get counted twice in list 3, but not each of them gets counted. And you could check this because if you look for the sum, if I sum a third and 1/6, this does not equal 1. If I look at these sums, this equals 1, and this equals 1 because every outcome has been counted once, but list 3 is not a good list because it does not equal 1. Any questions on a complete probability list? So we want to then find out here in list 1 and list 2, what other probability do I need to talk about to complete the list? So here's my robotics team. Boys, girls, middle school aged. So list 1 says, what's your probability of getting a boy? Well, reduced down is 3/5. What would be the other probability that would need to be involved in that list to complete that list? Right?
Isn't it the probability of not getting a boy?
So what is...
Getting a girl?
Yeah. So we could add to this list the probability of choosing a girl, which do you know the probability? I bet you know it without even looking at your sample space.
Wait, what was the boys one?
Boys is 3 out of 5.
2 out of 5.
Yeah.
We know it has to add up to 1. So since I know this is the only other option, that has to be 2/5. I could go back and check it. I got a girl here, girl there, and girl there, which is really 4 out of 10, which reduces to 2/5. But because we know that they have to add up to 1, I know it has to be 2/5. So check out list 2 for a second. What probability would have to be added to that list to make it equal 1, or really what is the only outcome not looked at? Olivia?
Older than 12.
Yeah. We have younger than 12. We have at age 12. So older than 12. And if this was 3/10 and this was 3/10, how many tenths are left over? 4/10. So that really actually reduces to 2/5. Any questions on how we complete the list? We need every outcome counted for and only once. My probabilities sum to 1. Why is this not a complete probability? Take a minute, check it out for yourself. I'll give you actually like probably 30 seconds. Write your own answer out. Actually, take a moment to write your answer. I'll give you longer than 30.
Are we gonna do the problem solving afterwards?
That one's pretty quick.
Problem solving.
The homework is pretty easy.
Why is this not a complete probability? James, what do you think? You've had your hand up for a minute.
It doesn't have the probability for an even number.
It doesn't involve the probability for an even. So if we have odd, we don't have even. What else?
Also, they didn't include blue.
Also, they didn't include blue, but I see that, well, they did include one of my blues. One of my blues would have been an odd. Let's look at the sections that they've counted. Probability of being red. So I'm going to put marks. So this is 1, and this is 1. Then probability of being odd. Well, I've got an odd here. This is odd again. This is again. Oh, now I count my 5. And then probability of being yellow. Well, now I count this again. Have I counted every outcome once? No.
No, you
Have any outcomes been counted more than once?
Yeah.
Yeah, so this is wrong multiple different ways. So they don't count every outcome, and some outcomes are counted more than once. So that is why this is not a complete probability. So you could say every outcome needs to be counted only once. could we make a complete table here? What could our options be to make a complete table where it would end up adding up to 1? Shahid?
Red, blue, and yellow.
Yeah, probability of red, blue, and then yellow. 3 different probabilities. What else? How else could I break this up? Nate?
Odds and evens.
Odds and evens. You got a different one? Are there any others? We did colors. We did odds or evens. Shahid?
I'm not sure.
You prime numbers.
We could do prime versus
What's the other one?
Composite.
composite. We could do prime versus composite. We could.
Numbers divisible by a specific other number.
Yeah, so we could do numbers divisible by or not. We could also do numbers less than or greater than that. Like, we could break it up a bunch of different ways as long as every outcome would only be counted once. Now, a uniform, what's it mean to be uniform? Why do you wear uniforms?
To look nice.
Peyton, why are you in a uniform? You got your jersey on today. When you're why does your coach make you all wear uniforms? So you match, so you look the same. So uniform, a synonym we want to use there is same. If we have a uniform probability, that means they are all going to have the same chance of happening. What are some examples of uniform probabilities that we've talked about? Nate?
Flipping a coin.
Flipping a coin. Each outcome has what percent chance when we flip a coin? 50%. What other uniform probabilities have we talked about? Pranav? Rolling a die. What's the odds of getting an outcome on a die? 1/6. What else? What about in a deck of cards? Do we have uniform probability there?
Oh yeah, red and black.
When you choose red versus black. What about when you choose suits? Is that uniform probability?
Yeah.
Yeah, what about when you choose specific card? Yeah, as long as each outcome is equally likely. So we're a city planner now. You've gone to college, or at least some kind of post-secondary, maybe an associate's degree or something like that. You're a city planner. So the city planner wants to know, is there a uniform probability of these cars turning left, going straight, or turning right? Do not compare situation A to B. They don't really relate, so only look at situation A right now. City planner wants to know the probability that a car waiting at the stop sign will turn left, go straight, or turn right. I can actually zoom back in on this.
1/3.
How many outcomes do I have?
3.
Three possible, right?
Well, 4. You could drive backwards.
No, you cannot. That's illegal. I think you're annoying your peers today. You need to back it up a little bit. So, will every outcome be equally likely?
Wait,
We're talking about cars at an intersection making a choice of where they go. Pranav?
but he's on the right lane, so he would be more.
That's the only lane he can be in right now.
Never mind.
Make sure you take a driver's ed course.
It's
Jackson.
a one-way road.
Hey, I can't hear Jackson, which is a big problem because you guys are all being rude.
So in a city, I know like if I don't know, like maybe in Chicago there might be some really big thing and we might want to go there, and somebody else might want to go there, and so it kind of depends. Like if there's something really big that a lot of people go to and they're turning right to get to it, then
So let's say that to the right is some big attraction, some like carnival or space center or something. Let's say that going straight takes you out to the highway, and let's say going left takes you into a neighborhood. Do you think it's equally likely that people will go to the big attraction, to the highway, and into the neighborhood? Yeah. So what I'm trying to get you to get at here is, one, we're missing a lot of information.
Yeah.
We've not been given very much information here as a city planner, but if you were at the intersection, maybe you could figure this information out. But what we're really trying to look at is, will a car go right, then go straight, then go left, then go right, then go straight, then go left, then go right? No, this is not going to be a uniform probability because they're not equally likely. So first off, we're missing information, but second off, these are not equally likely. So it's not uniform because they're not equally likely. if we stood there and collected some data, some experimental probability, they might be close, but I really doubt it. Because it especially matters what is each direction. Why are you not writing anything? Literally everybody else is. Yeah, we're now on the back of the paper. You don't even know where we're at in our notes. So yeah, I'm kind of picking on you because you're not with us at all. Write down what we just wrote down. Staring at me is not going to fix your past behavior. Shahid.
I was glancing at the second one.
Okay, so you're getting ahead of us. Glancing at the second one. So let's move on to situation B. So what is situation B, Shahid?
When friends walking and at each intersection they randomly choose from 3 slips.
So you are super bored this summer, and you're bothering your mother, and you're like, you keep bugging her, and finally your mom's like, I've had it. Get out of this house. Here you go. She hands you 3 slips of paper. She's like, you have to go for a walk. You're like, go for a walk.
Long walk.
Because you guys complain about everything. So, I'm making generalizations, I know. But this is an interesting idea, and it could actually be kind of fun. So your mom hands you 3 slips of paper. One says left, one says right, one says straight. She says you have to go for a walk, and every time you hit an intersection, you have to pull a slip of paper, and that will determine where you go. Now, of course, don't leave your neighborhood or whatever restrictions you have. Be safe, stay on the sidewalk, all that sort of stuff. But will the probability of each outcome in situation B be equally likely? Peyton, you're shaking your head now. Why?
The other one said it wasn't equally likely, and it's kind of the same thing.
What do you mean? Are you making the choice at the intersection? Did the drivers in their cars, were they making the choice? Mm-hmm. So, situation A, the choice was being made. How is the outcome being determined in situation B? Random draw. In a random draw situation, is each outcome equally likely, or is one outcome more favorable than others? They're all going to be equally likely. So this is actually a complete probability model, and they are uniform. Because I'm drawing them at random, this is the biggest thing. We're drawing them at random. This makes it uniform. Every outcome has what chance? 1/3. Every outcome has a 1/3 chance. So then your probability down at the bottom asks, what's the probability that you'll turn left, go straight, or turn right? It's 1/3. Each option is 1/3. Questions, comments, concerns? I don't really like situation A here, so we're going to skip it because there's too many variables that we can discuss. There are only 2 outcomes, but the argument every time we talk about this is how do you know how likely it, like, people like to talk about center of gravity. It has a larger center of gravity at the bottom, so it's got a lower center of gravity, but it depends on how you look at the push pin. So situation A, that's just kind of confusing. Too many variables. Situation B though, color cube has 2 red faces and 4 yellow faces. Suppose we roll the cube. What's the probability that the cube will land with a yellow facing up? Is this a uniform probability is what I want to ask first. Is every possible outcome equally likely? Shahid? No.
And it's 4/6 for the how likely yellow is going to be.
Yeah, your probability of yellow, you have 4 yellow faces over 6 total. So that can also reduce to 2/3. But because I see that the probability of getting yellow is 2/3, that's not uniform. So although every face is equally likely, because it's a number cube, that doesn't make it uniform. You have to look at what's the probability of each outcome. The outcome probabilities have to be equal. Yeah.
Like to make it uniform, you have to add like either another color or you would have to add another color to
Or
a different color, right?
not necessarily. If I replace a yellow face with a red face, that would make it uniform.
If the whole thing is yellow, does that make it uniform?
Yeah. Because then each outcome has a 100% chance of happening if the whole thing was yellow. Or I could make 2 of my faces blue, but I'd have to make 2 of my yellows blue because then I'd have 2 yellow, 2 blue, and 2 red. So there's a few things that I could do to make this uniform. Hello. Go back. But right now it's not uniform because they're not equally likely. Do we get this? Does this make sense? Sweet. Let's move on to problem solving really fast, and then we probably barely have to touch on this. We're gonna even skip the randomizer problem. This is a really terrible game. If you design a game, design a better game than this. Well, so we'll look at this really, really quick. So you walk into this space, you hit a button, it randomly chooses an outcome for you. What's your probability of winning? 1 out of 5, right? What percent is that?
1/5, which is 20%.
20%. This situation reminds me of the casino. Could you win? Yeah. Is your probability of winning tiny? 20%. I don't know that I'd call that tiny. I'd say like the probability of me getting hit by lightning. That's a tiny probability. Very, very, very unlikely. It could happen, but it probably won't. I could win. I could win in not that many tries. But who will normally win?
The 5th person.
The game, right? Or the casino, or whoever's not me. If my probability of winning is 20%, most of the time somebody else is going to win. So I'm going to lose. So this is when I like to talk about the casino is designed to take your money. Every game at the casino has a probability of you winning that is less than 50%. Now some of them are close. Like roulette or those games where it's like pretty close outcomes. Some of them are close, but no game at the casino has a probability of winning over, actually probably even over 48%. Because even if you walk up to the roulette wheel and just guess black or red, which your payout is not very high, but even if you just guess black or red, your percent chance of winning, I'm pretty certain, is 48%. Which is pretty good, right? You have a 48% chance of winning. That's not bad. But what that means, though, is the house is the casino, they have a 52% chance of winning, or at least a 52% chance of you losing, which is all they care about. They're not actually trying to win anything. So even if you win a few times, more often than not, the house will win and take your money. So only go to a casino if you plan on losing money. It's a fun time. I went to dinner this weekend and planned on spending money. So if you go to the casino and assume you will lose money and spend, it's okay. But don't go there expecting to win money. Then you're going to leave upset. Yeah, or just don't go at all, obviously. I'm trying to educate you guys for your future lives. Obviously, you're not going to the casino tomorrow.
Why is it illegal to count cards? Because that means they're losing.
It's not illegal. It's against the rules of the casino. Because it's a private establishment and they can create whatever rules they want. If I open a restaurant and it's a private establishment, I can say, like, you can't talk about my food. And I could kick you out if you do. Like, I can make whatever rules I want.
Was it like the restaurant in like Indiana that was like a Christian restaurant and they didn't want to cater?
I have no... Oh, you're talking about a bakery. So, which of these, talking about probability models that make sense, which of these options would make sense for choosing one student at random? The basketball coach has to choose a student after practice to clean up. He wants to choose a student to do the cleanup. Which of these situations would make sense? So, Karen, if we look at situation 1, I assign the 2 to represent the 6th graders, the 5 to represent the 7th graders, and the 3 to represent the 8th graders. Is that fair? What's the chance of a 2 happening on the spinner? 1/10, right? Chance of a 5 happening? 1/10. Chance of a 3 happening, 1/10.
What if it doesn't hit any of those?
So that one.
Would that work, Karen? So this is phrased a little weird. This is why I throw it to you guys, and I might change this for next year. This is saying he assigns the number 2 to represent both 6th graders. So if it lands on a 2, he chooses the 6th graders. He didn't choose one team member. This is not a good model because not only does it not choose a team member, it's not complete. He did not use all outcomes. He only used the 2, the 5, and the 3. So then if we look at option 2, Lily, if I use 0 and 1 to represent the 6th graders, well, how many 6th graders did I have? 2 6th graders, 0, 1. That seems to work. If I use 2, 3, 4, 5, 6 to represent the 7th graders, I had 5 of them, and we had 3 8th graders, 7, 8, and 9. Does that work, Lily?
Yes.
Yeah, so that model would work. That'd be a good one. What about model 3? Carrie, what do you think? Would model 3 work? Why does model 3 work? Yeah, they each have an equal chance. Is every outcome counted once? Yeah. And all my students are assigned to a number. And like Carrie said, they've got equal probabilities, equal chance of being chosen. So 2 or 3 are both essentially the same thing. You could argue that option 3 is a little bit more fair because it spreads out the 7th graders instead of them all being right next to each other on the spinner. If we spread them out, then maybe the 7th graders will have nothing to complain about, but I'm sure you guys could find something to complain about. Last thing we'll do today, because this relates a lot, and if you did the problem solving, you probably realize this. Sometimes data is okay to look at individual sections, and sometimes to get accurate results, we need to look at all of our data together. So, I want you guys to quickly figure out what's the probability of turning left for each of these different times of the day, and then combine all of your data together for the whole day probability of turning left. So Seth, how do I find the probability of turning left for my first table there?
You add them all together.
I add them all together. So what'd you get when you found the sum?
I got 110.
110. So is that my numerator or my denominator?
Denominator.
Denominator, what goes on my numerator?
38.
The amount of people that did turn left, and that comes out to be...
I didn't get to it.
So if we do 38 divided by 110, did anyone get it yet? Right, get that for us real fast if you would. I see you going.
This.
0.345.
Yeah.
So we know that's approximately 35%. And they say only if the percent's greater than 50 will we need a light. So we know, well, not in the morning we don't. Ella, how do I set up my probability for the middle of the day? What fraction do I have there? 52 over 109, you said? 101. This is why I ask. Should have worn earplugs when I was younger. Earplugs are really important. You guys don't realize it now, but if you're at like loud concerts or something, you should throw some in. And I know because of number sense, 52 over 100 would be just 0.52. So this will be very close to 0.5. It's probably 0.519. 518. Okay, but if I round it, it's 0.52. And my last one here, 25 over... So these are 49, 59. 25 over 59. Jackson?
0.42.
What is it?
0.42.
0.3.
What?
Two.
0.423, you mean?
Yeah.
Yeah, so that'd be about 42.3% when I move my decimal. Now, how do I find my combined probability? No?
I didn't find it, but I'm just. Do you just add all the denominators and all the numerators together?
Take all your probabilities of turning left and your total for everything. So really, like Pranav said, since I already did it broken up, I can take all my numerators and add them together. Anyone do it yet?
200. No, wait.
100.
200. What is it?
260.
The numerator is 115.
115.
Yeah.
And my denominators,
I can do this.
it's 211 plus 59.
270. 60. 260. 270? It's one of those two.
270.
270.
See, I knew it.
Do your 111 plus 9 takes you to
Yeah.
120. Then add the 50.
I should have 100.
So what do we get here when we combine them together? 115 over 270? Jackson?
22 over 54.
Well, okay, I don't... Decimal.
Oh, 42 and...
So would I need a light?
No.
No. The only time of the day that it would maybe be necessary is in the middle of the day.
You'd barely be necessary.
But yeah, so I would probably want to collect some more data before I go ahead and make that decision. Maybe this day just had extra traffic, or maybe this day was a light traffic day, and maybe I do need a light. But with the data that we have collected from this day, it does not look like we would need to suggest installing a light.
A month.
3 month, or, yeah.
Just like a month.
You can't just do one day.
Yeah, exactly. Like one day would be hard to argue that it's
It could be
accurate.
like construction, or it could be a car crash.
Man, we don't really have much. I was hoping we'd have more time than this. We have like 7 minutes. I can unlock the cart if you want, or we could just do Mine Trap.
Can you do
Yes,
my
my trap.
Mine trap.
Mine trap. Mine trap.
No, but I want to.
All the homework is already posted.